Right now, at this very moment, you are falling through time at exactly 1 second per second. That rate is fixed, unchangeable, as constant as anything in your experience. But near a black hole, time does something impossible. It breaks. If you were to fall toward the event horizon of a supermassive black hole, while someone watched from a safe distance, your clock and their clock would disagree so violently that the numbers become almost meaningless. 1 second for you, 10,000 years for them. One heartbeat measured by your watch. 10,000 trips around the sun measured by theirs. This is not science fiction. This is not speculation. This is a consequence of Einstein's general relativity, confirmed by every experiment we have ever conducted on the behavior of gravity and time. In 1915, Albert Einstein published his general theory of relativity. The mathematics were elegant but strange, predicting that gravity was not a force pulling objects together, but rather a warping of space-time itself. Mass bends the fabric of reality. The more massive the object, the deeper the bend. And where space-time bends, time itself flows differently. Clocks tick at different rates depending on how deep they sit in a gravitational well. Einstein's own colleague Karl Schwarzschild, while serving on the Russian front during World War I, found the first exact solution to Einstein's field equations. He calculated what would happen around a point mass compressed to infinite density. The mathematics showed something extraordinary. There exists a boundary now called the Schwarzschild radius, or event horizon, where space-time curves so severely that time from an outside observer's perspective appears to stop completely. Schwarzschild died of an illness contracted in the war just months after publishing his solution in 1916. He never knew that his equations described objects we now call black holes. The physics underlying this time dilation is straightforward to state, but profound to contemplate. Space-time is not a backdrop against which events occur, but rather a dynamic fabric that responds to mass and energy. Near a massive object, this fabric stretches and warps. Imagine space-time as a flexible surface, though this is just an analogy. Place a heavy ball on a stretched rubber sheet, and the sheet curves downward. Roll a marble near the depression, and it follows the curved surface. That curvature is gravity. But the curvature affects not just space, but time as well. Deeper in the gravitational well, time itself moves more slowly relative to someone farther out. This is gravitational time dilation. We measure it with atomic clocks placed at different altitudes on Earth. A clock on the ground ticks more slowly than a clock on a mountaintop by a tiny amount, just nanoseconds per day. But the effect is real, measurable, and must be accounted for in the Global Positioning System satellites orbiting above us. Without corrections for both gravitational and velocity-based time dilation, GPS coordinates would drift by kilometers within hours. Near a black hole, this effect amplifies to extremes that seem to violate our intuition about reality. The mathematics show that as you approach the event horizon, the gravitational time dilation grows without bound. At the horizon itself, time dilation becomes infinite from the perspective of a distant observer. They watch you fall. You accelerate towards the black hole. But as you approach the horizon, they see you slow down. Your movements become sluggish. Your light redshifts to longer and longer wavelengths as your photons climb out of the deepening gravitational well. From the distant observer's perspective, you take longer and longer to cross each meter. You approach the horizon asymptotically, never quite reaching it, your image freezing in place and fading to darkness as the light redshifts beyond visibility. But this is their perspective, not yours. From your perspective, falling freely toward the black hole, nothing unusual happens at the event horizon. You cross it in finite time measured by your own watch. For a supermassive black hole like Sagittarius A star at the center of our galaxy, with a mass 4 million times that of the Sun, you might have minutes or even hours of free fall before reaching the horizon. You feel no particular boundary, no membrane or wall. The horizon is defined entirely by light's inability to escape, not by any physical substance. You pass through it. But while you experience this finite journey measured in seconds or minutes by your own clock, the universe outside is aging at an accelerated rate. The degree of acceleration depends on how close you are to the horizon. Very near the horizon, the time dilation factor approaches infinity. 1 second for you corresponds to an arbitrarily large time outside. Here is the calculation that produces the 10,000-year figure. Consider a black hole with the mass of our Sun compressed to a Schwarzschild radius of about 3 kilometers. The time dilation factor at a distance r from the center is given by the square root of 1 minus the Schwarzschild radius divided by r. As you approach the Schwarzschild radius, this factor grows. At a distance where you are hovering, say, just a tiny fraction above the horizon, the time dilation becomes enormous. If you position yourself close enough that the time dilation factor is 10,000, then for every second you experience, 10,000 seconds pass for someone far from the black hole. That is not 10,000 seconds. That is about 2 hours and 47 minutes. But the effect scales. Position yourself even closer and the factor becomes 1,000,000, 1,000,000,000. There is no limit except the horizon itself. Scientists have verified this effect through observations of matter orbiting close to black holes. X-ray binary systems, where a black hole or neutron star pulls matter from a companion star, provide natural laboratories. The hot gas spiraling into the black hole emits X-rays whose spectrum and timing reveal the extreme environment near the event horizon. Observations by NASA's Rossi X-ray Timing Explorer and the European Space Agency's XMM Newton satellite have measured how X-ray emissions from these systems fluctuate on millisecond timescales. The flickering light carries signatures of matter orbiting at substantial fractions of the speed of light in regions where gravitational time dilation is significant. The measurements match the predictions of general relativity with remarkable precision. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the dark circle at the center of the galaxy M87. The shadow's size and shape confirmed that space-time near the horizon behaves exactly as Einstein's equations predict. This creates a profound asymmetry in the experience of time. If you were to fall toward a black hole and somehow survive the tidal forces, you could, in principle, watch the universe age rapidly. Light from distant stars would blue shift as you fall deeper into the gravitational well. If you fell slowly, hovering just above the horizon using rocket thrust to resist the pull, you could remain there while millennia pass outside. You age years. The universe ages eons. When you finally escape, if escape were possible, you would return to a cosmos transformed beyond recognition. Stars would have died and been born. Civilizations would have risen and fallen. This is not time travel in the sense of moving backward, but it is a profound decoupling of your timeline from the timeline of the rest of the universe. The effect depends on the mass of the black hole in a counterintuitive way. Supermassive black holes produce less severe tidal forces at their event horizons than stellar mass black holes. The gravitational gradient, the change in gravitational pull from your head to your feet, decreases with increasing black hole mass. For a black hole with 1 billion solar masses, you could cross the horizon without being torn apart by tidal forces. You would simply fall through, experiencing time dilation just as extreme but surviving the approach. For a solar mass black hole, the tidal forces would shred you long before you reach the horizon. Your feet, closer to the singularity, would be pulled far more strongly than your head. The stretching, called spaghettification, would disintegrate your body. But the time dilation would occur regardless. The universe outside would still age rapidly compared to your brief, final moments. This raises questions about information and causality that physicists still debate. If you fall past the event horizon, the light you emit can never reach an outside observer. From their perspective, you never quite cross. You fade and freeze. But from your perspective, you do cross, and quickly. This apparent contradiction is resolved by recognizing that the two perspectives describe different slices of space-time. There is no universal now. Your now deep in the gravitational well is not the same as the now of someone far away. The structure of space-time itself prevents a consistent definition of simultaneity across regions with different gravitational potentials. What is simultaneous depends on your path through space-time. Before you drift off, leave a comment. What time is it where you are right now, and where in the world are you watching from? The answer depends on more than you might think. The mathematics describing this effect emerged directly from the Schwarzschild metric, the solution to Einstein's field equations for a non-rotating black hole. The metric defines the geometry of space-time. It tells you how to measure distances and time intervals in the curved space-time around the black hole. The time component of the metric includes the factor that produces gravitational time dilation. That factor depends only on your distance from the center and the mass of the black hole. It does not care about your velocity or acceleration, only your position in the gravitational field. This is a purely geometric effect. The curvature of space-time itself determines how clocks tick. Real black holes rotate, which adds complexity. In 1963, Roy Kerr found the exact solution to Einstein's equations for a rotating black hole. The Kerr metric introduces additional effects beyond simple time dilation. Space-time itself gets dragged around the rotating black hole in a phenomenon called frame dragging. Near the horizon of a rotating black hole, it becomes impossible to remain stationary relative to distant stars. You are forced to orbit in the direction of the black hole's rotation. This creates an ergosphere, a region outside the event horizon where the rotational energy of the black hole can theoretically be extracted. But the time dilation effects remain, amplified by the rotation in certain regions. Observations suggest that most astrophysical black holes rotate rapidly, with angular momentum approaching the maximum allowed by general relativity. The implications extend beyond black holes. Any strong gravitational field produces time dilation. Neutron stars with masses comparable to the Sun compressed into spheres just 20 kilometers across create gravitational fields strong enough to slow time by measurable amounts. Pulsars, rotating neutron stars that emit beams of radio waves, provide cosmic clocks. The precision timing of pulsar signals has confirmed gravitational time dilation and other predictions of general relativity with extraordinary accuracy. The binary pulsar system, PSRB 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974, showed two neutron stars orbiting each other. The system loses energy exactly as predicted by the emission of gravitational waves, and the time dilation effects in the strong mutual gravitational fields match Einstein's equations. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. These extreme time effects force us to reconsider what we mean by the present moment. If two events are simultaneous for one observer but not for another, and both perspectives are equally valid, then simultaneity is not a fundamental property of events, but rather a consequence of the observer's motion and gravitational environment. This realization undermines the intuitive notion of a universal now, a cosmic present that marches forward uniformly everywhere. Instead, space-time is a four-dimensional structure in which different observers carve out different definitions of time and space depending on their trajectories. The present moment for someone falling into a black hole encompasses events in the distant future of someone watching from afar. These are not contradictory statements, but rather reflections of the geometric structure of curved space-time. The prospect of using black holes for time dilation raises possibilities that seem to belong to science fiction, but rest on solid physics. If you could orbit close to a black hole's event horizon without falling in, you could age slowly while the universe outside ages rapidly. This would require tremendous energy to maintain the orbit against the pull of gravity, energy proportional to how close you hover to the horizon. The closer you orbit, the more extreme the time dilation, but the more energy you need to avoid falling in. For a spacecraft with finite fuel, there are limits to how long you could maintain such an orbit. But in principle, the effect is real. You could use a black hole as a time machine to the future, though not to the past. This connects to the broader question of how time itself works at the most fundamental level. The conventional understanding of time treats it as absolute, universal, ticking forward at the same rate everywhere. This is the time of Isaac Newton, the time of everyday experience, the time your body feels as it ages 1 second after another. But this understanding breaks down completely in the presence of strong gravity. Time is not absolute. Time is relative. And the mechanism that makes it relative involves nothing less than the fundamental structure of reality itself. At the heart of this mechanism lies space-time, a four-dimensional fabric that combines the three dimensions of space with the single dimension of time into one unified entity. This is not a metaphor. This is the actual geometry that governs how the universe works. In flat space-time, far from any massive objects, the geometry is simple. The shortest path between 2 points is a straight line. Clocks tick at consistent rates. Light travels in straight paths, but introduce mass, and the geometry warps. The fabric curves. And in curved space-time, the rules change. General relativity describes gravity not as a force, but as curvature. Mass and energy tell space-time how to curve. Space-time tells matter how to move. This is the essence of Einstein's field equations, a set of 10 coupled nonlinear partial differential equations that relate the geometry of space-time to the distribution of matter and energy within it. The equations are elegant in their mathematical form, but ferociously difficult to solve in all but the simplest cases. The Schwarzschild solution for a non-rotating black hole and the Kerr solution for a rotating one represent rare exact solutions to these equations. Most realistic scenarios require numerical methods and supercomputers to approximate the behavior of space-time. The curvature affects time because time and space are fundamentally intertwined. When you measure a distance in space-time, you are measuring an interval that includes both spatial separation and temporal separation. The metric, a mathematical object that defines distances in curved space-time, includes components that mix space and time. Near a massive object, the time component of the metric changes. This change is what produces gravitational time dilation. A clock measures proper time, the time along its own path through space-time. Different paths accumulate different amounts of proper time. A clock deep in a gravitational well follows a path through more severely curved space-time than a clock farther away. The result is fewer ticks for the deeper clock when both paths are compared at the same space-time events. Here is where conventional understanding fails most dramatically. We expect time to be a backdrop, a stage on which events occur. We expect clocks everywhere to agree about how much time has passed between two events. But space-time does not work that way. There is no universal time coordinate. There is no cosmic clock ticking at the same rate everywhere. Every clock measures time along its own world line, its path through four-dimensional space-time. Two clocks that separate and then reunite will in general show different elapsed times. This is not an illusion or a measurement error. The clocks genuinely experience different amounts of time. The geometry of space-time makes it so. Think about this using a more familiar analogy. Imagine two hikers starting at the base of a mountain. One hiker takes a steep path directly up the slope. The other takes a gentle, winding path that circles the mountain. Both reach the summit. Both have traveled from the same starting point to the same ending point, but they have covered different distances. The hiker on the steep path might have walked 3 kilometers. The hiker on the winding path might have walked 10 kilometers. They started together and ended together, but the paths between were different lengths. In space-time, the equivalent of distance is proper time. Different paths through space-time accumulate different amounts of proper time, even when they connect the same events. The hiker who descends deep into a gravitational well and climbs back out experiences less proper time than the hiker who stays at a higher gravitational potential. Both age. Both experience time. But they age different amounts. The mechanism operates through what physicists call the gravitational redshift of time intervals. Consider a clock deep in a gravitational well, emitting light pulses at regular intervals, as measured by that clock. Each pulse climbs out of the gravitational well and reaches an observer farther away. The pulses arrive at the distant observer separated by longer time intervals than they were emitted. The light itself redshifts, its wavelength stretched by the climb out of the gravitational field. But more fundamentally, the time between pulses stretches. This is not because the pulses slow down during their journey. Light always travels at the speed of light in its local environment. The stretching occurs because time itself flows differently at different gravitational potentials. The clock deep in the well is ticking more slowly from the perspective of the distant observer. The pulses are emitted at longer intervals as measured by the distant observer's time, even though they are emitted at identical intervals as measured by the emitting clock's time. We can measure this effect with extraordinary precision using atomic clocks. In 1971, Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners and compared them to atomic clocks that remained on the ground. The flying clocks, experiencing less gravitational time dilation at altitude and also relativistic time dilation due to their velocity, showed measurable differences from the ground clocks when the flights were complete. The differences amounted to just hundreds of nanoseconds, but they matched the predictions of general relativity and special relativity within experimental error. This was one of the first direct confirmations that gravitational time dilation is real and measurable with technology available in the early HE. Modern atomic clocks have become far more precise. Optical lattice clocks, which trap individual atoms in grids of laser light and measure their oscillations at optical frequencies, can detect time dilation differences over height changes of just 1 centimeter. In 2010, researchers at the National Institute of Standards and Technology in Boulder, Colorado, showed that an optical clock raised by 33 centimeters ticks measurably faster than an identical clock left at the original height. The difference is tiny, about 90 parts in 1 quintillion, but it is measurable and matches the predictions of general relativity. These clocks are sensitive enough to measure the curvature of space-time itself over human scales. The fundamental forces and particles involved in this phenomenon are subtle. time dilation is not mediated by a particle in the way that electromagnetism is mediated by photons or the strong nuclear force by gluons. Gravity in general relativity is the curvature of space-time itself, not a force transmitted by particles. Attempts to quantize gravity and describe it in terms of hypothetical particles called gravitons remain incomplete and speculative. At the scales where general relativity applies, gravity is pure geometry. The presence of mass-energy curves space-time. That curvature dictates how objects move and how time flows. The particles and fields that make up matter respond to this curvature, following geodesics, the straightest possible paths through curved space-time. A freely falling object experiences no force in its own reference frame. It is simply following the natural geometry of space-time. But this geometric description of gravity creates tensions with quantum mechanics, the theory that governs the behavior of particles at microscopic scales. Quantum mechanics treats time as an absolute background parameter. The Schrödinger equation, which governs how quantum states evolve, assumes a universal time coordinate. But general relativity denies that such a coordinate exists. Reconciling these two pillars of modern physics remains one of the deepest unsolved problems in theoretical physics. Near the event horizon of a black hole, both quantum effects and strong gravitational curvature become important. The singularity at the center of a black hole, where densities and curvatures become infinite in the classical theory, is almost certainly a place where quantum gravity effects dominate. We do not have a complete theory of quantum gravity, so we do not truly understand what happens at the singularity. General relativity breaks down. The predictions become meaningless. Something else must take over, but we do not yet know what. The measurable effects of time dilation extend to phenomena we observe across the universe. Gravitational lensing, where light from distant galaxies bends around massive foreground objects, is a direct consequence of space-time curvature. The light follows geodesics through curved space-time, and those geodesics bend around the massive object. The bending can produce multiple images of the same background galaxy, arcs of distorted light, or even complete rings called Einstein rings. Observations of gravitational lensing confirm that space-time curves exactly as general relativity predicts. The time delays between different images of a lensed object also reveal time dilation effects. Light taking different paths through the curved space-time around the lensing mass experiences different gravitational potentials and thus different amounts of time dilation. The delays can be measured and compared to models, providing another test of the theory. Detecting time dilation near black holes requires observing matter in extreme environments. X-ray binaries, where a black hole accretes matter from a companion star, emit X-rays from the hot inner regions of the accretion disk. The X-ray emissions flicker on timescales of milliseconds, reflecting processes occurring in regions where orbital velocities approach the speed of light and gravitational time dilation is severe. By analyzing the timing and spectrum of these X-rays, astronomers can map the space-time geometry near the event horizon. The ion emission lines in the X-ray spectrum are particularly useful. The lines are broadened and skewed by the extreme velocities and gravitational effects near the black hole. The shape of the line profile reveals the spin of the black hole and confirms that space-time behaves as general relativity predicts. The history of understanding these effects begins with Einstein, but extends through decades of theoretical and observational work that transformed our view of the universe. Einstein published his special theory of relativity in 1905, addressing the relationship between space and time for observers moving at constant velocities relative to each other. The theory showed that time is not absolute, that moving clocks tick more slowly, and that simultaneity depends on the observer's reference frame. But special relativity applied only to inertial frames, observers not experiencing acceleration. Gravity remained outside the theory's scope. Einstein spent the next decade struggling with the problem of how to incorporate gravity into the relativistic framework. The breakthrough came between 1912 and 1915, as he learned the mathematics of curved surfaces and differential geometry. He realized that gravity could be understood as the curvature of space-time itself. Mass tells space-time how to curve. Curved space-time tells matter how to move. The field equations he published in November 1915 encoded this insight in mathematical form. The first experimental confirmation came startlingly quickly. In 1919, Arthur Eddington led expeditions to observe a total solar eclipse from Príncipe Island off the coast of West Africa and from Sobral in Brazil. The eclipse would allow astronomers to photograph stars near the sun's edge, stars normally invisible in the sun's glare. General relativity predicted that the sun's mass would curve spacetime, bending the light from those stars and making them appear slightly displaced from their true positions. Newton's theory of gravity also predicted a deflection, but only half as large. Eddington's photographs showed deflections consistent with Einstein's prediction of 1.75 arcseconds for light, grazing the sun's surface. The announcement made Einstein world-famous overnight. Newspapers proclaimed that space was curved and time was relative. The measurements were not perfect. Later analysis suggested the error bars were larger than Eddington acknowledged, but subsequent observations during later eclipses confirmed the effect with greater precision. The early theoretical understanding of black holes developed slowly. Schwarzschild's 1916 solution described the geometry around a point mass, but physicists initially viewed the infinite curvature at the Schwarzschild radius as a mathematical pathology rather than a prediction of physical reality. The singularity at the center, where densities and curvatures become infinite, seemed absurd. Many physicists assumed that something would prevent the formation of such objects. In 1939, Robert Oppenheimer and Hartland Snyder published a paper showing that a massive star, having exhausted its nuclear fuel, would collapse under its own gravity and form what we now call a black hole. The collapse from the perspective of a distant observer would appear to slow and freeze at the event horizon, but the collapsing matter itself would pass through in finite time and continue to the singularity. Their work demonstrated that black holes were inevitable consequences of general relativity, not mere mathematical curiosities. The term black hole did not enter widespread use until 1967, when physicist John Wheeler popularized it during a lecture. Before that, these objects were called frozen stars or collapsed stars or dark stars. The name black hole captured the essential feature, a region of space-time from which nothing, not even light, can escape. Wheeler's advocacy helped shift black holes from theoretical speculation to objects that astronomers might actually find. The question became not whether black holes exist, but where to look for them. The breakthrough in detection came through X-ray astronomy. In 1964, a rocket-borne X-ray detector discovered a powerful X-ray source in the constellation Cygnus, designated Cygnus X-21. By 1971, astronomers had identified a blue supergiant star at that location, orbiting an invisible companion every 5.6 days. The orbital dynamics implied that the unseen companion had a mass of at least 10 solar masses. No known object except a black hole could be that massive and remain invisible. The companion was accreting matter from the supergiant star, heating the infalling gas to millions of degrees and producing the X-rays. Cygnus X1 became the first widely accepted black hole candidate. Stephen Hawking famously bet against its being a black hole in 1974, a bet he conceded in 1990 as the evidence became overwhelming. Through the ANDE, astronomers discovered more X-ray binaries and began to distinguish between stellar mass black holes formed from collapsed stars and supermassive black holes, millions or billions of times more massive, residing in galaxy centers. In 1974, astronomers detected radio emissions from the center of our galaxy pointing to an extremely compact, massive object. By the hours, observations of stars orbiting this central object, designated Sagittarius A star, revealed that it must have a mass of about 4 million suns confined within a region smaller than the solar system. Only a supermassive black hole could fit these constraints. Andrea Ghez and Reinhard Genzel led teams that tracked individual stars orbiting Sagittarius A star over decades, watching them accelerate to thousands of kilometers per second as they swung close to the black hole. Their work earned them the Nobel Prize in Physics in 2020. The technological advances required to study black holes spanned multiple domains. Space-based X-ray telescopes, beginning with Uhuru, launched in 1970 and continuing through Einstein Observatory in 1978, ROSAT in 1990, Chandra in 1999, and XMM Newton in 1999, provided the sensitivity to detect X-rays from accreting black holes. Ground-based infrared and radio telescopes allowed astronomers to peer through dust and track objects in crowded galactic centers. Adaptive optic systems, developed in the ANDE, compensated for atmospheric turbulence and produced images sharp enough to resolve individual stars near Sagittarius A star. Interferometry, combining signals from multiple radio telescopes spread across continents or even the entire Earth, achieved resolutions far beyond what any single telescope could provide. The Event Horizon Telescope represents the culmination of this technological progression. The collaboration linked radio telescopes from Hawaii to Chile to Antarctica to Europe, creating a virtual telescope with an effective diameter equal to the Earth itself. The target was M87 star, the supermassive black hole at the center of the giant elliptical galaxy Messier 87, some 55 million light-years away. Observations in April 2017 captured radio emissions from the hot gas orbiting the black hole. Processing the data required sophisticated algorithms to combine signals recorded at different sites and reconstruct an image. The result, released in April 2019, showed a bright ring of emission surrounding a dark central region. The dark region is the black hole's shadow, created by light rays that curve so strongly near the event horizon that they either fall in or emerge in different directions. The shadow's diameter measured about 40 billion kilometers, consistent with a black hole mass of 6.5 billion suns. The image confirmed predictions made decades earlier about what a black hole's silhouette should look like. The evolution of theoretical understanding paralleled these observational advances. In 1963, Roy Kerr solved Einstein's equations for a rotating black hole, showing that rotation adds profound complexity to the space-time structure. A rotating black hole drags space-time around with it, creating the ergosphere where nothing can remain stationary. In 1974, Stephen Hawking discovered that quantum effects near the event horizon cause black holes to emit radiation, a process now called Hawking radiation. The radiation is extraordinarily faint for astrophysical black holes and has never been directly detected, but it implies that black holes are not completely black and will eventually evaporate over timescales vastly longer than the current age of the universe. A solar mass black hole would take 10 to the 67 years to evaporate, a Google times longer than the 13.8 billion years since the Big Bang. Numerical relativity, the use of supercomputers to solve Einstein's equations for dynamic situations like colliding black holes, matured in the eye. For decades, numerical simulations of black hole mergers crashed or produced nonsensical results due to instabilities in the equations. In 2005, multiple research groups independently achieved breakthroughs that allowed stable, long-term simulations. These simulations predicted the gravitational wave signals that merging black holes would produce. When LIGO detected gravitational waves from a black hole merger in September 2015, the observed signal matched the numerical simulations with astonishing precision. The merger involved black holes of 36 and 29 solar masses, spiraling together and forming a final black hole of 62 solar masses. The missing 3 solar masses converted into energy, radiated away as gravitational waves in a fraction of a second. The peak power output exceeded the combined light from all stars in the observable universe. LIGO's detections, numbering in the dozens by the early opened gravitational wave astronomy as a new way to study black holes. Unlike electromagnetic radiation, gravitational waves pass through matter almost unimpeded. They carry information about regions of spacetime where curvature is extreme and changing rapidly, regions that light cannot easily escape. The waves stretch and squeeze spacetime itself as they propagate, causing tiny changes in the distances between objects. LIGO detects these changes by measuring how the travel time of laser light changes along perpendicular arms several kilometers long. The sensitivity is extraordinary, detecting length changes smaller than 1/10,000th the diameter of a proton. Each detection confirms that black holes exist, that they merge, and that spacetime behaves exactly as general relativity predicts, even in these violent events. The mergers reveal black holes spinning at substantial fractions of the maximum possible rate. General relativity limits how fast a black hole can spin. The spin parameter ranges from 0 for a non-rotating black hole to 1 for a maximally rotating Kerr black hole. Measurements from X-ray observations and gravitational wave detections suggest that many black holes have spin parameters above 0.9, rotating at more than 90% of the maximum rate. This rapid rotation affects the surrounding spacetime, dragging it around and altering the orbits of nearby matter. The innermost stable circular orbit, the closest distance at which matter can orbit without spiraling inward, depends on the black hole's spin. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. For a maximally rotating black hole, the orbit can be as close as 1/2 the Schwarzschild radius, measured at the equator. Matter orbiting that close experiences extreme time dilation and gravitational effects. These discoveries over a century transformed black holes from speculative solutions to Einstein's equations into observed astrophysical objects whose properties match theoretical predictions with stunning precision. The time dilation effects predicted in 1915 and measured in 1971 with flying atomic clocks become extreme near event horizons in ways we can now observe through the light emitted by orbiting matter. The universe contains millions of stellar mass black holes in our galaxy alone, and supermassive black holes in the centers of most large galaxies. They are not rare, they are fundamental components of cosmic structure, and they warp spacetime so severely that the very flow of time itself becomes flexible, variable, dependent on where you are and how you move through the gravitational field. The broader context of these objects within the structure of the universe reveals even deeper connections between black holes, time, and the evolution of cosmic structure itself. Black holes do not exist in isolation. They are embedded in galaxies, They are embedded in galaxies connected to vast networks of dark matter and ordinary matter, participating in the evolution of cosmic structure across billions of years. The supermassive black holes at the centers of galaxies appear to be intimately linked to the properties of their host galaxies in ways that suggest a deep connection between the growth of these monsters and the formation of the galaxies themselves. This connection emerged from observations in the and early showing that the mass of a central supermassive black hole correlates tightly with properties of the surrounding galaxy, particularly the velocity dispersion of stars in the galactic bulge. The correlation is striking. Measure how fast stars move in the central bulge of a galaxy, and you can predict the mass of the central black hole to within a factor of 2 or 3. The relationship holds across galaxies spanning a wide range of masses, from dwarf galaxies with black holes of hundreds of thousands of solar masses to giant ellipticals with black holes exceeding 10 billion solar masses. The ratio of black hole mass to bulge mass sits around 0.1 to 0.2% with remarkable consistency. This tells us that black holes and galaxies must grow together, regulating each other's development through feedback processes that remain only partially understood. Gas falling into the black hole releases enormous amounts of energy as it heats up and radiates. This energy, in the form of intense radiation and powerful jets, can blow gas out of the galaxy, quenching star formation and limiting both the galaxy's growth and the black hole's own growth by cutting off the fuel supply. This feedback mechanism operates on scales ranging from the immediate vicinity of the black hole, measured in light days or light weeks, to the entire galaxy spanning hundreds of thousands of light years. The active galactic nuclei, or AGN, powered by accreting supermassive black holes, represent the most energetic persistent phenomena in the universe. A quasar, the bright core of a galaxy with an actively feeding supermassive black hole, can outshine the entire galaxy by factors of hundreds or thousands. The radiation comes from the accretion disk, the swirling maelstrom of gas spiraling into the black hole. Friction within the disk heats the gas to millions of degrees. The inner regions where matter orbits at substantial fractions of the speed of light and time dilation become significant, emit X-rays and ultraviolet light. The outer regions emit visible and infrared radiation. The combined output can reach luminosities of 10 trillion times the sun's brightness, all from a region smaller than the solar system. The jets launched by some supermassive black holes extend for millions of light years, creating enormous lobes of radio emission and shock-heating intergalactic gas. These jets carry energy outward from the black hole's immediate environment, depositing it across vast distances and affecting the evolution of galaxy clusters. The mechanism that produces the jets involves magnetic fields threading the accretion disk and the black hole's ergosphere. The rapidly rotating black hole and the orbiting magnetized plasma twist the magnetic field lines into helical structures that channel matter and energy outward along the rotation axis at speeds approaching the speed of light. The Blandford-Znajek process, proposed in 1977, describes how energy can be extracted from a rotating black hole via magnetic fields, converting the black hole's rotational energy into the kinetic energy of the jet. Observations confirm that the most powerful jets come from rapidly rotating black holes. How black holes fit into the larger cosmic web involves their role in both galaxy mergers and the overall distribution of matter. Galaxies merge frequently in the early universe and less frequently in the later universe. When two galaxies collide and merge, their central black holes eventually sink to the center of the merged system and form a binary black hole. The two black holes orbit each other, gradually losing energy to gravitational waves and interactions with surrounding stars and gas. Eventually, they merge in a violent event that releases tremendous energy as gravitational waves. The LIGO and Virgo detectors have observed dozens of stellar mass black hole mergers, but supermassive black hole mergers remain undetected. The gravitational waves from such events have frequencies too low for ground-based detectors. Future space-based detectors like the Laser Interferometer Space Antenna, planned for launch in the teens, should detect supermassive black hole mergers out to cosmological distances. The paradoxes and connections multiply when considering time dilation in the context of these cosmic structures. An observer falling into the supermassive black hole at the center of a galaxy experiences their own time normally. But from the perspective of someone far from the black hole, the infalling observer's clock slows dramatically as they approach the horizon. Light from the infalling observer redshifts to longer and longer wavelengths. The last photon emitted just before crossing the horizon takes an infinite amount of time to reach the distant observer, asymptotically approaching them but never quite arriving in finite time. Yet the infalling observer crosses the horizon quickly by their own clock. This creates an apparent paradox. From one perspective, the crossing never happens. From another, it happens immediately. The resolution lies in understanding that space-time itself has a structure that makes these both true statements about different slices through the four-dimensional geometry. Measurement challenges in studying black holes stem from their fundamental property of being black. We cannot see the black hole itself, only its effects on surrounding matter and light. The event horizon emits nothing. The shadow seen by the Event Horizon Telescope is not the horizon itself, but rather the boundary of the region from which photons can escape. Photons emitted just outside this boundary can spiral around the black hole multiple times before escaping, creating complex light patterns. Photons emitted inside the photon sphere, a region at 1.5 times the Schwarzschild radius for a non-rotating black hole, inevitably either fall into the black hole or orbit forever. The shadow we observe is larger than the event horizon itself, extended by this region where light cannot escape to distant observers. Secondary effects of extreme gravity near black holes include the frame dragging already mentioned, and also gravitational lensing on multiple scales. Light from objects behind the black hole bends around it, sometimes forming complete rings if the alignment is perfect. More commonly, the black hole magnifies and distorts background sources. The lensing allows us to probe the mass distribution around the black hole and test whether the space-time geometry matches the predictions of general relativity. So far, every measurement confirms Einstein's theory. The departures from Newtonian gravity near the event horizon are dramatic, factors of thousands or millions, yet the observations match the relativistic predictions with precision, limited only by measurement uncertainties. Our position relative to black holes matters profoundly for what we can observe and measure. The nearest stellar mass black holes lie hundreds or thousands of light-years from Earth. The nearest supermassive black hole, Sagittarius A star, sits about 26,000 light-years away at the galactic center. We orbit the galaxy at a safe distance, in a relatively quiet suburban region where star formation proceeds at a modest rate, and the radiation environment is benign enough for complex chemistry and life. Closer to the galactic center, the stellar density increases, as does the background radiation from the central black hole and from massive stars. The tidal forces from the central black hole become significant within a few light-years. Stars occasionally wander too close and get torn apart by tidal forces in events called tidal disruption events. The disruption creates a brief bright flare as the stellar material forms an accretion disk and falls into the black hole. Astronomers have observed dozens of these events in other galaxies using optical and X-ray telescopes. Location matters for time dilation in a direct way. If you lived on a planet orbiting close to a black hole, you would age more slowly than someone living farther away. The difference could be dramatic. A planet orbiting at the innermost stable circular orbit around a supermassive black hole would experience time flowing at perhaps half the rate of someone far from the black hole. 10 years on the planet would correspond to 20 years for the distant observer. This is not theoretical speculation. It is a mathematical consequence of the metric describing space-time around the black hole. Such planets are unlikely to exist, as the environment near a black hole is hostile to planet formation and stability. But the principle holds. Your location in the gravitational field determines how fast your clock ticks relative to other clocks at different locations. The gravitational potential well of Earth itself produces measurable time dilation. Clocks at sea level tick more slowly than clocks on mountaintops by about 10 nanoseconds per day per kilometer of altitude difference. GPS satellites orbit at altitudes of about 20,000 kilometers. At that altitude, gravitational time dilation causes their clocks to tick faster than ground clocks by about 45 microseconds per day. Velocity-based time dilation from their orbital motion causes them to tick slower by about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. Without corrections for these relativistic effects, GPS position errors would accumulate at a rate of about 10 kilometers per day. The system would be useless within hours. The corrections are implemented in the satellite system software and hardware, a routine application of general and special relativity to everyday technology. This interplay between gravity, time, and measurement extends to cosmological scales. The universe itself has a large-scale structure shaped by gravity, acting over billions of years. Dark matter, which interacts only through gravity, dominates the mass distribution. It forms filaments and halos within which galaxies form and evolve. Black holes participate in this structure as endpoints of stellar evolution and as the central engines of galaxies. The time dilation near black holes represents an extreme version of a universal phenomenon. Wherever there is mass, space-time curves, and time flows at a rate determined by that curvature. The challenges of measuring time dilation directly near black hole event horizons remain formidable, but the indirect evidence is overwhelming. The spectrum of X-rays from accretion disks, the orbital dynamics of matter spiraling inward, the gravitational wave signals from mergers, and the shadow image from the Event Horizon Telescope all confirm that space-time near black holes behaves exactly as general relativity predicts. These predictions include the extreme time dilation that makes 1 second for an observer near the horizon correspond to years or millennia for someone far away. This time dilation creates tension with our attempts to measure fundamental cosmic parameters, a tension that reveals deep questions about how the universe expands and evolves. The extreme time dilation near black holes creates a fundamental tension at the heart of modern physics, a conflict between two of our most successful theories that show but catastrophically do not. On one side stands general relativity, Einstein's geometric theory of gravity that has passed every experimental test for more than a century. On the other side stands quantum mechanics, the probabilistic framework governing the behavior of particles and fields at microscopic scales. Both theories work extraordinarily well within their domains. But near the event horizon of a black hole, where space-time curves severely and quantum effects become important, the two theories make predictions that cannot simultaneously be true. This conflict threatens our understanding of reality itself. General relativity describes what happens to an observer falling into a black hole with mathematical precision. The approach begins with Einstein's field equations and the solutions that describe black hole spacetime, particularly the Schwarzschild metric for non-rotating black holes and the Kerr metric for rotating ones. These solutions tell us that an observer in free fall crosses the event horizon in finite proper time, the time measured by a clock traveling with the observer. For a supermassive black hole with a mass of 1 billion suns, an observer falling from rest at a large distance would cross the horizon in about 5 hours of proper time. Nothing special happens at the crossing. The horizon is not a physical surface, but merely a mathematical boundary, marking the point of no return. The observer feels no force, sees no barrier, experiences no discontinuity. The tidal forces remain manageable for supermassive black holes, weak enough that the observer survives the crossing intact. General relativity predicts that the infalling observer smoothly continues toward the singularity at the center, where curvatures become infinite and the classical theory breaks down. This is the equivalence principle at work. Locally, in a small enough region around the falling observer, space-time looks flat and the laws of physics take their familiar special relativistic form. The observer should detect nothing unusual at the horizon. The numbers from general relativity are unambiguous. The metric coefficients at the event horizon remain finite in the frame of the infalling observer. The proper acceleration needed to hover at a fixed distance from the black hole diverges as you approach the horizon, becoming infinite exactly at the Schwarzschild radius. But for an observer in free fall, experiencing no acceleration, all physical quantities remain well behaved at the horizon crossing. The temperature of the surrounding space in the observer's frame stays finite. The energy density of any radiation present stays finite. General relativity gives a clear answer, verified by decades of mathematical analysis and numerical simulation. The horizon is smooth. The crossing is uneventful. The observer continues inward. Quantum mechanics approaches the same question from a completely different direction and arrives at an incompatible conclusion. The starting point is Hawking's discovery in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. Virtual particle pairs spontaneously appear near the horizon due to quantum fluctuations. Normally, these pairs annihilate immediately. But near the horizon, one particle can fall into the black hole while the other escapes to infinity, becoming real radiation. The process slowly drains energy from the black hole, causing it to evaporate over enormous timescales. For a stellar mass black hole, the evaporation time exceeds the current age of the universe by factors of 10 to the 50 or more. But the principle remains. Black holes are not eternal. They radiate and eventually disappear. The quantum mechanical analysis reveals a profound problem. The Hawking radiation appears to be purely thermal, containing no information about what fell into the black hole. Thermal radiation has maximum entropy for a given energy. It carries no distinguishing features, no way to reconstruct what created it. If you burn a book and a pile of wood, both produce thermal radiation, but the radiation from the book contains no recoverable information about what words were printed on its pages. Hawking radiation seems to work the same way. The black hole could have formed from a collapsing star, a collection of elementary particles, or anything else with the same total mass and angular momentum. The radiation that eventually emerges looks identical in all cases. This means that information has been destroyed. A pure quantum state, describing the matter that formed the black hole with complete specificity, has evolved into a mixed thermal state that has lost all memory of its origin. The total information content of the universe has decreased. This contradicts a fundamental principle of quantum mechanics called unitarity. Quantum evolution is supposed to be reversible. If you know the quantum state of a system at one time, you can in principle calculate it at any other time, forward or backward. Information is preserved. The equations of quantum mechanics are deterministic in this sense, even though individual measurements yield probabilistic outcomes. Destroying information violates unitarity. It breaks quantum mechanics. And if quantum mechanics is broken, the entire framework we use to understand particle physics, chemistry, and much of modern technology collapses. The stakes could not be higher. The disagreement between these two approaches is not a small numerical discrepancy. It is a fundamental conceptual conflict. General relativity says the horizon is smooth and empty, just curved vacuum. Quantum mechanics says the horizon must be energetic enough to prevent information loss, potentially violent enough to destroy anything trying to cross. The conflict sharpened dramatically in 2012 when physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully proposed the firewall paradox. They argued that if information is preserved in Hawking radiation, as quantum mechanics demands, then the event horizon cannot be the smooth, empty boundary that general relativity predicts. Instead, infalling observers must encounter a wall of high-energy radiation at the horizon, a firewall that incinerates anything attempting to cross. This conclusion follows from requirements about how quantum information must be distributed between the Hawking radiation and the black hole interior if unitarity holds. The firewall argument relies on quantum entanglement, the phenomenon where particles can share quantum states in ways that defy classical description. When Hawking radiation is emitted, each escaping particle is entangled with its partner that fell into the black hole. But if the radiation is to carry away information about what formed the black hole, it must also be entangled with the earlier radiation already emitted. A quantum system cannot be maximally entangled with two different systems simultaneously. This is the monogamy of entanglement. Something has to give. The firewall proposal says that at some point, the entanglement between the escaping particle and its infalling partner must be broken. Breaking this entanglement requires energy, potentially enormous energy densities concentrated at the horizon. This energy appears as the firewall, a barrier that contradicts the equivalence principle's promise of a smooth horizon crossing. Why both frameworks should agree but do not comes down to the incompatibility between quantum mechanics and general relativity. Quantum mechanics treats space-time as a fixed background on which fields and particles evolve. General relativity treats space-time itself as a dynamical entity that responds to matter and energy. Near the event horizon, both the quantum properties of matter and the dynamic properties of space-time become crucial. We need a theory of quantum gravity to resolve the conflict, but no such theory exists in complete form. String theory, loop quantum gravity, and other approaches remain incomplete or untested. The firewall paradox exposes this gap in our understanding with brutal clarity. We can calculate what general relativity predicts. We can calculate what quantum mechanics requires. The two calculations give contradictory results. Both cannot be right. How the extreme time dilation near the horizon factors into this debate adds another layer of complexity. The time dilation means that different observers have radically different notions of when events occur. For the distant observer watching someone fall into the black hole, the crossing takes infinite time. The infalling observer appears to freeze at the horizon, never quite crossing from the outside perspective. But from the infalling observer's perspective, the crossing happens in finite proper time, minutes or hours depending on the black hole mass. This disagreement about the timing of events makes it difficult to formulate consistent statements about what happens at the horizon. Does the firewall appear instantly when the black hole forms, from the perspective of a distant observer? Or does it emerge gradually over the black hole's evaporation time? The answers depend on whose time coordinate you use, and there is no preferred choice. The implications for our physical models are profound. If the firewall is real, then the equivalence principle fails in a fundamental way. Local physics near the horizon would not reduce to special relativity. The smooth geometric picture of general relativity would break down. We would need to revise our understanding of how gravity works in strong field regimes. If instead there is no firewall and the horizon remains smooth, then we need to explain how quantum information escapes from the black hole interior, where by definition, nothing can escape. Some proposed resolutions involve subtle correlations in the Hawking radiation that encode information without violating causality. Others suggest modifications to quantum mechanics itself. Still others invoke exotic possibilities like traversable wormholes connecting the black hole interior to distant regions of spacetime. The stakes extend beyond black holes themselves to the foundations of physics. Understanding what happens at a black hole event horizon requires reconciling quantum mechanics and gravity, which means developing a complete theory of quantum gravity. Such a theory would describe physics at the Planck scale, where both quantum effects and gravitational effects become comparable in strength. The Planck length is about 10 to the minus 35 meters, far smaller than anything we can directly probe with current technology. The Planck energy is about 10 to the 19 billion electron volts, far higher than any particle accelerator can reach. Black holes provide natural laboratories where quantum gravity effects become important at scales we can observe, at least in principle. The event horizon of a stellar mass black hole has a radius of a few kilometers, enormous compared to the Planck length, but the combination of intense curvature and the requirement that quantum mechanics applies to fields in curved spacetime brings quantum gravity into the picture. Observations cannot yet distinguish between these scenarios. The Hawking radiation from astrophysical black holes is far too faint to detect with any foreseeable technology. The temperature of the radiation scales inversely with the black hole mass. For a solar mass black hole, the temperature is about 60 nanokelvin, billions of times colder than the cosmic microwave background. The radiation is completely swamped by other sources. Only primordial black holes, if they exist with masses below about 10 to the 11 kilograms, would be hot enough to emit detectable radiation, and even then the signal would be faint. No such black holes have been detected. We cannot directly test whether firewalls exist or whether information is preserved in Hawking radiation. The debate remains theoretical, grounded in mathematical consistency arguments rather than experimental data. This creates a frustrating situation where our two best theories of fundamental physics make incompatible predictions about a regime we cannot directly observe. The resolution will likely require theoretical breakthroughs rather than new observations. We need to understand how to consistently combine quantum mechanics and general relativity. The time dilation near black holes, extreme but calculable within general relativity, becomes problematic when we ask what the time-dilated infalling observer sees in terms of quantum fields and radiation. Does the observer see the universe age rapidly due to time dilation effects? Does the blue-shifted radiation from the distant universe create a fireball? These questions touch on the interface between the two theories and remain unresolved. The counterintuitive aspects of this situation deepen when we consider that the horizon location itself depends on the observer and on the global structure of spacetime. The event horizon is not a physical object you can touch or a membrane stretched across space. It is a coordinate surface, a mathematical boundary defined by light's inabile find, by light's inability to escape. This distinction creates one of the most counterintuitive features of black hole physics. The horizon exists at different locations depending on which coordinate system you choose to describe spacetime. In Schwarzschild coordinates, the coordinates most commonly used by distant observers, The horizon sits at a specific radius where time appears to stop. But in coordinates adapted to an infalling observer, coordinates that fall along with matter entering the black hole, the horizon simply does not exist as a special location. The geometry remains smooth. Nothing marks the point of crossing. The observer glides through without incident, at least according to classical general relativity. This seems backwards because we expect physical phenomena to have physical causes. A boundary that destroys information or incinerates observers should be made of something, should have energy density, should create detectable effects. But the equivalence principle, one of the founding ideas of general relativity, insists that an observer in free fall cannot detect the gravitational field locally. A small laboratory falling freely in Earth's gravity feels weightless. Experiments inside the laboratory yield the same results as experiments performed in empty space, far from any gravitating mass. Einstein used this principle to conclude that gravity is not a force, but rather the curvature of space-time itself. Applied to a black hole horizon, the equivalence principle says that free fall across the horizon should feel like free fall anywhere else. Locally, in a small enough region, space-time is flat. The observer detects nothing unusual, yet the global structure of space-time near the horizon is anything but ordinary. The distinction between local and global becomes crucial. Locally, in a region small enough that tidal forces are negligible, physics looks normal. Globally, considering the entire space-time geometry, the horizon represents a profound boundary. Light emitted outward from just inside the horizon does not escape to infinity. It curves back inward, falling toward the singularity. Light emitted just outside the horizon can escape, though heavily redshifted by the climb out of the gravitational well. The difference between these two regions is not a difference in local physics, but in the large-scale causal structure of space-time. Events inside the horizon are causally disconnected from events outside in the sense that no signal from inside can ever reach outside. Think about this using an analogy with flowing water. Imagine a river flowing toward a waterfall. Far upstream, the water flows slowly, and you can easily paddle against the current. Closer to the waterfall, the current strengthens. At some point, the flow velocity equals your maximum paddling speed. If you are exactly at this point, you can maintain position by paddling upstream at full strength. This critical distance is analogous to the photon sphere around a black hole, where light can orbit at a fixed radius. Beyond this point, closer to the waterfall, the current exceeds your paddling ability. No amount of effort allows you to escape. You are swept toward the edge. The point where the current speed equals your maximum speed is analogous to the event horizon. Once you cross it, escape becomes impossible not because of any physical barrier, but because the flow of space-time itself carries everything inward faster than light can travel outward. The horizon is not a wall. It is the boundary where the geometry of space-time changes in a global sense. The observational evidence for event horizons comes indirectly through the behavior of matter and light near black holes. We cannot see the horizon itself, but we can see its effects. The shadow imaged by the Event Horizon Telescope in M87 shows a dark central region, surrounded by a bright ring of emission. The dark region corresponds to the photon sphere, the boundary within which light cannot escape to distant observers. Computer simulations of accretion disks around black holes predict exactly this appearance. The simulations solve the equations of general relativity together with the equations governing magnetized plasma dynamics. They calculate how photons emitted from different parts of the accretion disk travel through curved spacetime to reach a distant observer. The resulting images match the observed shadow size and shape with remarkable precision. the black hole mass inferred from the shadow diameter, about 6.5 billion solar masses, agrees with independent estimates from the dynamics of gas and stars orbiting the black hole. Simulations of matter falling into black holes reveal subtle differences from naive expectations. You might expect that matter simply falls straight in, accelerating smoothly toward the singularity. But magnetic fields thread the accretion disk, and these fields interact with the plasma in complex ways. The simulations show that matter does not fall radially inward, but rather spirals, following magnetic field lines that themselves twist and reconnect in chaotic patterns. Near the horizon, frame dragging from the black hole's rotation forces the magnetic fields and plasma to rotate with the black hole. This rotation can launch jets along the black hole's spin axis, where frame dragging effects are weakest. The jets carry energy and angular momentum away from the system, a process that paradoxically allows more matter to fall into the black hole by removing the angular momentum that would otherwise keep it orbiting. The statistical improbability of certain observed features provides evidence that our models are incomplete. Some active galactic nuclei exhibit variability on timescales of minutes, implying that the emission comes from regions smaller than a few light minutes across. For a supermassive black hole, the event horizon radius is typically measured in light hours or light days. The emission region is far smaller than the horizon itself. This tells us that the energy generation occurs in the inner accretion disk, very close to the innermost stable circular orbit. The physics in this region includes effects like Doppler beaming, gravitational lensing, and extreme time dilation that cause the observed brightness to fluctuate rapidly as hotspots in the disk orbit the black hole. Simulating these effects requires solving Einstein's equations on curved spacetime, while simultaneously tracking the emission and propagation of photons. The computational demands are enormous, but the results match observations well enough to give confidence that the models capture the essential physics. Alternative frameworks for understanding black holes have been proposed to avoid the paradoxes associated with event horizons and information loss. One approach suggests that the event horizon is replaced by a dynamical surface just above where the classical horizon would form. This surface, sometimes called a firewall or a quantum atmosphere, has enough energy density to radiate information and prevent a true horizon from forming. Infalling matter would be destroyed by intense radiation before reaching the nominal horizon radius. This preserves unitarity by ensuring that information never truly enters a causally disconnected region. But it violates the equivalence principle by placing a high-energy surface at a location where general relativity predicts only empty curved spacetime. Observations have not detected such a surface, though detecting it would require resolving structures near the event horizon with far greater precision than current instruments can achieve. Another alternative involves modified theories of gravity that alter general relativity at strong field scales. These theories introduce additional fields or change the relationship between curvature and matter in ways designed to avoid singularities or event horizons. Some modified theories predict that what we call a black hole is actually a very compact object with a surface just above the Schwarzschild radius, a surface dense enough and reflective enough to mimic an event horizon, but not quite forming one. Such objects are sometimes called gravastars or black stars. They would emit light from the surface, though very faintly due to extreme gravitational redshift. The light would be redshifted by factors of millions or billions, shifting visible light down to radio wavelengths and making the object appear dark in most observations. Distinguishing these alternatives from true black holes requires observations with sensitivity and resolution beyond what we currently possess. The fuzzball proposal from string theory suggests that black holes are not empty spacetime surrounding a singularity, but rather highly excited quantum states of strings and branes, filling the entire region where the horizon would classically form. From a distance, these fuzzballs would look nearly identical to classical black holes. But they would have no interior, no singularity, and no information paradox, because the infalling information is absorbed into the quantum state of the fuzzball itself. The fuzzball radiates thermally like a Hawking black hole, but the radiation carries subtle correlations that encode information about what fell in. This preserves unitarity without requiring a firewall at the horizon. The fuzzballs remain speculative because string theory itself remains incomplete and untested at the energies where quantum gravity becomes important. Each alternative framework addresses some aspects of the black hole paradoxes while introducing new questions or tensions with observations. The firewall preserves quantum mechanics, but breaks general relativity. Modified gravity theories avoid singularities but require departures from Einstein's equations that have not been detected. Fuzzballs resolve the information paradox but rely on string theory, which has no experimental confirmation. The classical black hole picture matches all current observations but leads to the information loss problem and the firewall paradox. Choosing between these frameworks requires either new observations or theoretical breakthroughs that clarify which aspects of each picture are essential and which are artifacts of incomplete understanding. The role of time dilation in these alternatives varies. In some models, the extreme time dilation near the horizon is exactly as general relativity predicts. In others, modifications to spacetime structure at small scales alter how time flows in strong gravitational fields. Measuring time dilation directly near a black hole event horizon would require sending clocks close to the horizon and comparing their readings to distant clocks. The technical challenges are overwhelming with current technology. The closest approach would subject the clock to intense tidal forces and radiation. Retrieving the data would require transmitting signals out of the deep gravitational well, where they would be severely redshifted and weakened. The experiment remains in the realm of thought experiments rather than practical proposals. Nevertheless, the principle of time dilation near horizons is on firm theoretical ground and indirectly confirmed through observations of orbital dynamics and emission spectra from accretion disks. Matter orbiting close to the innermost stable circular orbit experiences time dilation factors of 2 or more compared to distant observers. The orbital frequency, as measured by a distant observer, is lower than the frequency measured in the orbiting material's own frame by exactly this time dilation factor. X-ray observations show spectral features whose widths and shifts encode information about the orbital velocities and time dilation in the emission region. These observations match the predictions of general relativity without requiring modifications or alternatives. The question of whether the horizon is truly smooth or conceals a firewall remains open. The answer will likely come from theoretical progress rather than observation. We need to understand how quantum fields behave on curved space-time backgrounds and how space-time itself responds to quantum fluctuations. This is the domain of quantum gravity, where our current theories reach their limits. Until we have a complete theory that unifies quantum mechanics and general relativity, the fundamental nature of event horizons will remain uncertain. But the time dilation effects, extreme and counterintuitive as they are, appear robust across all proposed frameworks. 1 second near the horizon corresponds to thousands or millions of seconds far away, regardless of whether the horizon is empty vacuum, a firewall, or a quantum fuzzball. The techniques we use to measure and infer these extreme effects rely on precision observations across the electromagnetic spectrum, from radio waves to gamma rays, and more recently, on gravitational wave detections. Measuring the effects of extreme gravity near black holes demands instruments sensitive enough to detect photons that have climbed out of gravitational wells so deep that their energy has been cut to a fraction of what they carried when emitted. The techniques span wavelengths from meter-long radio waves to gamma rays, with wavelengths smaller than atomic nuclei. Each wavelength regime reveals different aspects of the physics near the event horizon. Radio observations trace the large-scale structure of jets and the shadow of the black hole itself. Infrared observations penetrate dust to reveal stars orbiting close to supermassive black holes in galactic centers. Optical and ultraviolet observations capture the thermal emission from outer accretion disk regions. X-rays probe the hottest, innermost regions where relativistic effects dominate. Gamma rays reveal the most energetic processes, though their sources near black holes remain only partially understood. The transformation of observational astronomy accelerated dramatically in the beginning with the advent of space-based instruments. Earth's atmosphere blocks most electromagnetic radiation except visible light, some radio wavelengths, and narrow infrared windows. X-rays from cosmic sources cannot reach the ground. They are absorbed high in the atmosphere. The first cosmic X-ray source beyond the solar system, Scorpius X-1, was detected in 1962 by a sounding rocket, carrying Geiger counters above the atmosphere for a few minutes. That brief flight opened a new window on the universe. By the early dedicated X-ray satellites like Uhuru, launched in 1970, were conducting systematic surveys. Uhuru discovered more than 300 X-ray sources, including numerous X-ray binaries, where compact objects accrete matter from companion stars. The high-energy radiation provided the first clear evidence that stellar mass black holes exist in our galaxy. NASA's Chandra X-ray Observatory, launched in 1999, and the European Space Agency's XMM Newton, launched the same year, represent the current state-of-the-art in X-ray astronomy. Chandra achieves angular resolution better than 1 arcsecond, comparable to ground-based optical telescopes, using nested cylindrical mirrors that reflect X-rays at grazing incidents. The telescope orbits Earth in a highly elliptical path, taking it more than 130,000 kilometers from the planet, far beyond the radiation belts that would create background noise in the detectors. XMM Newton has larger collecting area and better spectral resolution, allowing detailed studies of X-ray emission lines. Together, these observatories have observed thousands of black hole candidates in our galaxy and beyond, measuring the X-ray spectra and timing with precision sufficient to test general relativity in strong gravitational fields. Information extraction from X-ray spectra relies on understanding how radiation interacts with matter in extreme conditions. The inner accretion disk around a black hole reaches temperatures of millions to tens of millions of degrees. At these temperatures, atoms are completely ionized. Electrons stripped from nuclei scatter X-ray photons. Ion nuclei, having lost most or all of their electrons, produce characteristic X-ray emission lines when electrons transition between energy levels in the highly ionized atoms. The ion K-alpha line produced when an electron drops into the innermost shell of an ion appears at an energy of 6.4 kilo-electron volts in a stationary iron atom. But iron orbiting close to a black hole is not stationary. It moves at substantial fractions of the speed of light. The orbital motion produces Doppler shifts. Iron moving toward us emits blue shifted photons with higher energy. Iron moving away emits red-shifted photons with lower energy. Gravitational redshift from the deep potential well adds another effect, shifting all photons to lower energies as they climb out to reach our telescopes. The result is a broadened, skewed emission line extending from about 2 or 3 kilo-electron volts up to 7 or 8 kilo-electron volts, far wider than the narrow line from stationary iron. The detailed shape of this broad iron line encodes information about the geometry of spacetime near the black hole. The amount of broadening depends on the orbital velocities, which depend on the radius of the inner edge of the accretion disk. The inner edge typically coincides with the innermost stable circular orbit. For a non-rotating black hole, this orbit sits at 3 times the Schwarzschild radius. For a maximally rotating black hole, it can be as close as 1/2 the Schwarzschild radius measured at the equator. The iron line profile thus reveals the black hole's spin. High spin means the inner disk extends closer to the horizon, meaning higher velocities and more extreme broadening and redshift. Observations of iron line profiles in dozens of systems show spin parameters ranging from nearly 0 to values exceeding 0.9, with many supermassive black holes rotating rapidly. The characteristic scales involved span enormous ranges. The Schwarzschild radius for a solar mass black hole is about 3 kilometers. For the supermassive black hole in M87, with a mass of 6.5 billion suns, the Schwarzschild radius is about 19 billion kilometers, roughly 130 times the Earth-Sun distance. The accretion disk extends from near the innermost stable circular orbit, a few times the Schwarzschild radius, out to perhaps thousands or millions of Schwarzschild radii in the outer regions. The hottest emission comes from the innermost regions. The temperature scales inversely with radius. Material at the innermost stable circular orbit around a stellar mass black hole can reach temperatures of 10 million degrees. Around a supermassive black hole, the same orbital radius produces cooler temperatures, around 100,000 degrees, because the gravitational acceleration is weaker for the same radius measured in Schwarzschild radii. This temperature difference explains why stellar mass black holes emit primarily in X-rays, while supermassive black holes emit across broader wavelength ranges, including ultraviolet and optical light. Independent confirmation of black hole properties comes from gravitational wave observations. The LIGO and Virgo detectors measure gravitational waves by monitoring the interference pattern of laser light traveling along perpendicular arms several kilometers long. When a gravitational wave passes through the detector, it stretches space along one arm while compressing it along the other. The arm lengths change by a tiny amount, less than 1,000th the diameter of a proton over a 4-kilometer arm. The interference pattern shifts, and that shift encodes the gravitational wave signal. The first detection, announced in February 2016 but recorded in September 2015, came from 2 black holes of 36 and 29 solar masses spiraling together and merging. The event occurred 1.3 billion light-years away. The gravitational wave signal lasted about 0.2 of a second, sweeping upward in frequency from 35 to 250 Hz as the black holes orbited faster and faster before merging. The waveform shape matched predictions from numerical relativity simulations with extraordinary fidelity. The simulations solve Einstein's field equations on supercomputers to calculate how spacetime evolves during a black hole merger. The calculation is extraordinarily complex because the equations are nonlinear. The curvature of spacetime depends on the distribution of energy, but gravitational waves themselves carry energy, creating a feedback loop where the waves alter the spacetime through which they propagate. Despite this complexity, the simulations accurately predicted the observed signal. The match allowed scientists to infer the masses of the merging black holes, their spins, the distance to the merger, and even the orientation of the orbital plane. The final black hole, with a mass of 62 solar masses, has 3 solar masses less than the sum of the initial masses. That missing mass converted to energy and radiated away as gravitational waves in a fraction of a second. Recent advances in X-ray timing analysis have revealed quasi-periodic oscillations in the emission from black hole accretion disks. These oscillations, detected in dozens of systems, show up as periodic or quasi-periodic variations in the X-ray brightness, with frequencies ranging from millihertz to kilohertz. The highest frequency oscillations, occurring hundreds of times per second, likely originate from the innermost regions of the accretion disk, where orbital periods are shortest. For a stellar mass black hole of 10 solar masses, the orbital period at the innermost stable circular orbit is about 1 millisecond, corresponding to a frequency of 1000 Hz. Observed quasi-periodic oscillations in some systems reach frequencies approaching this limit, providing further evidence that the inner disk extends down to the innermost stable orbit, and confirming that the strong field dynamics match general relativity predictions. Precision improvements in radio interferometry culminated in the Event Horizon Telescope observations. The technique of very long baseline interferometry combines signals from radio telescopes separated by continental or intercontinental distances. The effective angular resolution equals the resolution of a single telescope, with a diameter equal to the separation between the dishes. The Event Horizon Telescope linked 8 facilities, including the Atacama Large Millimeter Array in Chile, the South Pole Telescope in Antarctica, the Submillimeter Telescope in Arizona, and telescopes in Hawaii, Mexico, and Spain. The maximum baseline stretched nearly 11,000 kilometers, creating a virtual telescope with an effective diameter approaching the size of Earth. At the observing wavelength of 1.3 millimeters, this baseline provides angular resolution of about 20 micro-arcseconds, fine enough to resolve structure on scales comparable to the event horizon of the M87 black hole. The data recorded at each site filled hard drives with petabytes of information. The observations occurred in April 2017 over several nights. The data could not be transmitted electronically due to the enormous volume. Instead, the hard drives were physically shipped to central processing centers in Massachusetts and Germany, where supercomputers correlated the signals. The correlation process involves finding the precise time delays between signals arriving at different telescopes, delays caused by the geometric configuration of the telescope array, and Earth's rotation. The processing required months of computation. The resulting image, released in April 2019, showed the bright ring of emissions surrounding the black hole shadow with remarkable clarity. The ring diameter measured 42 micro-arcseconds, consistent with the predictions for a black hole of 6.5 billion solar masses at a distance of 55 million light-years. Future observations promise even greater precision and new capabilities. The Event Horizon Telescope collaboration is working to add more stations, including facilities in Africa and additional sites in the Northern Hemisphere. More stations improve the coverage of the virtual aperture and allow reconstruction of higher fidelity images. Observing at shorter wavelengths, around 0.87 millimeters instead of 1.3 millimeters, would improve the resolution further and allow observations when atmospheric conditions at 1.3 millimeters are poor. The next generation Event Horizon Telescope might resolve structure within the emission ring, seeing variations in brightness that trace the orbital motion of hotspots in the accretion disk. Such observations could measure frame-dragging effects around rotating black holes and test general relativity in the strong field regime with unprecedented precision. Space-based X-ray observatories planned for the WIL have collecting areas tens of times larger than Chandra or XMM Newton. The proposed Advanced X-ray Imaging Satellite and the European Athena mission, now called New Athena, would observe fainter sources and measure spectra with better energy resolution. These missions could detect iron line profiles from black holes in distant galaxies, extending measurements of black hole spin to cosmological distances. They could also observe transient events like tidal disruption events, where a star wanders too close to a black hole and gets torn apart, with sufficient sensitivity to track how the debris forms an accretion disk and eventually falls into the black hole. These observations would test whether matter behaves as general relativity predicts during the entire infall process, from initial disruption at several Schwarzschild radii down to the plunge through the innermost stable circular orbit. Gravitational wave detectors will also advance significantly. The current LIGO detectors are being upgraded to higher sensitivity through the Advanced LIGO Plus program. The upgrades include better mirrors, more powerful lasers, and quantum techniques to reduce noise from photon counting statistics. The improved detectors will observe black hole mergers at greater distances and with better signal-to-noise ratios, allowing more precise measurements of black hole masses and spins. The European Virgo detector and the Japanese Kagra detector are also being upgraded. Together, these ground-based detectors will form a global network capable of localizing gravitational wave sources to small patches of sky, enabling electromagnetic telescopes to quickly follow up and search for any light emitted during the merger. The Laser Interferometer Space Antenna, a joint NASA-ESA mission planned for launch in the mid-SE, will detect gravitational waves at frequencies between 0.1 MHz and 1 Hz, far lower than ground-based detectors can access. These low frequencies correspond to gravitational waves from merging supermassive black holes with masses from millions to billions of suns. Such mergers produce gravitational wave signals that last for months or years, building up in amplitude and frequency as the black holes spiral inward. LISA will detect these mergers years before the final coalescence, providing advance warning of when and where to look for electromagnetic counterparts. The mission will consist of 3 spacecraft, flying in a triangular formation, each separated by 2.5 million kilometers, far from Earth's gravitational and seismic noise. The laser links between spacecraft will measure distance changes with picometer precision, sensitive enough to detect gravitational waves from supermassive black hole mergers across the entire observable universe. These future observations will probe time dilation effects indirectly through their influence on orbital dynamics and radiation emission. Material orbiting close to a black hole experiences time flowing more slowly from a distant observer's perspective. This means the orbital frequency appears lower to the distant observer than it would in flat spacetime at the same radius. The magnitude of the effect depends on the gravitational potential, which depends on the black hole mass and the orbital radius. By measuring orbital frequencies and comparing them to predictions, we test whether time dilation occurs as general relativity predicts. Every observation so far confirms the predictions. The iron line profiles, the quasi-periodic oscillations, the gravitational wave signals, and the event horizon shadow all show time dilation effects consistent with Einstein's equations. The accumulated weight of these measurements across different wavelengths, different types of sources, and different observational techniques provides overwhelming evidence that spacetime near black holes behaves as general relativity describes. The extreme time dilation that makes 1 second near the horizon correspond to years or millennia far away is not speculation. It is a direct consequence of spacetime curvature, confirmed by every relevant observation. Understanding this effect in specific systems, from stellar mass black holes in our galaxy to supermassive ones in distant galaxies, reveals the diversity of black hole properties while confirming the underlying physics. The diversity of black holes across the universe, profiles across the universe, provides natural laboratories for testing how time dilation operates under different conditions. stellar mass black holes formed from collapsed stars, intermediate mass black holes whose origins remain mysterious, and supermassive black holes anchoring galaxy centers, all warp space-time around them according to the same equations. But the details differ in ways that reveal how mass, spin, and environment shape the extreme gravitational effects. Comparing specific systems shows patterns and outliers that challenge our understanding while confirming the basic framework of general relativity. Cygnus X1 remains the best-studied stellar mass black hole, observed continuously since its X-ray emission was first detected in 1964. The system consists of a blue supergiant star designated HDE 226868, with a mass of about 40 suns orbiting an invisible companion every 5.6 days. The orbital dynamics require the companion to have a mass of approximately 21 solar masses, firmly above the maximum mass for a neutron star. This makes Cygnus X1 a black hole by elimination. No other known object can be that massive and remain invisible. The black hole accretes matter from the stellar wind of the supergiant, pulling gas into an accretion disk that heats to millions of degrees and emits X-rays. Observations over decades have revealed that the system transitions between two distinct states. In the hard state, the X-ray spectrum is dominated by emission from a hot corona surrounding the inner disk. In the soft state, thermal emission from the disk itself dominates. The transitions between states occur irregularly, sometimes after months in one state, sometimes after just days. The spin of the Cygnus X1 black hole has been measured through analysis of the X-ray continuum spectrum and ion emission lines. Multiple independent measurements using different techniques converge on a spin parameter of approximately 0.95, meaning the black hole rotates at 95% of the maximum rate allowed by general relativity. This rapid rotation has profound consequences for the space-time geometry. The innermost stable circular orbit sits at about 1.5 times the Schwarzschild radius, rather than 3 times for a non-rotating black hole. Matter can orbit closer to the event horizon, experiencing more extreme velocities and time dilation. The frame-dragging effect is strong enough that space itself is dragged around the black hole at substantial fractions of the speed of light, out to distances of several Schwarzschild radii. Photons emitted from the inner disk experience gravitational lensing and Doppler beaming effects that concentrate their energy toward observers viewing the system at certain angles. GRS 1915-05 represents an even more extreme case. This stellar mass black hole, discovered in 1992 by the Granite satellite, exhibits X-ray variability on timescales from seconds to months. The black hole mass is estimated at about 14 solar masses, orbiting a companion star every 33 days. What makes this system special is its extraordinarily high luminosity. At times, GRS 1915-105 emits X-rays at rates approaching the Eddington limit, the maximum luminosity at which radiation pressure balances gravity and prevents further accretion. The system also launches powerful jets that emit radio waves detectable from Earth. Observations with radio interferometry have measured the apparent velocities of knots of material moving outward in the jets at speeds exceeding the speed of light, as measured across the plane of the sky. This superluminal motion is a geometric effect, not a violation of relativity. Material moving toward us at nearly the speed of light covers most of the distance to a new position before the light from the new position reaches us, making it appear to have traveled faster than light between observations. The true velocity is just below the speed of light, but the geometry creates the illusion of faster motion. V404 Cygni provides contrast to these high-spin systems. This black hole, with a mass of about 9 solar masses has a measured spin parameter of just 0.2, indicating slow rotation. The system goes through decades-long quiescent periods punctuated by brief outbursts when accretion suddenly increases. During an outburst in June 2015, the system brightened by factors of thousands in optical and X-ray light over a few weeks. The rapid brightening allowed detailed observations of how the accretion disk forms and evolves. Surprisingly, the observations revealed that the inner accretion flow precesses, wobbling like a spinning top, with a precession period of just a few hours. This precession likely results from the misalignment between the black hole's spin axis and the orbital plane of the binary system. The precessing disk creates time-varying shadows and beaming effects that cause the observed brightness to fluctuate dramatically. Supermassive black holes show equally diverse properties despite their common location at galaxy centers. Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, is remarkably quiet. It accretes matter at a very low rate, producing only faint radio and X-ray emission. The luminosity is billions of times lower than the Eddington limit. Gas falling towards Sagittarius A star appears to be extremely hot and diffuse, with temperatures reaching billions of degrees. At these temperatures, the gas emits very little radiation per unit volume. Most of the gravitational potential energy released as matter falls inward goes into heating the gas rather than radiating away. Observations of stellar orbits around Sagittarius A star have provided the most precise measurements of a black hole mass using purely dynamical methods. The star, designated S2, has an orbital period of 16 years and approaches within 17 light-hours of the black hole at closest approach. In 2018, observations captured S2 at its closest point, moving at about 3% of the speed of light. The orbital motion showed gravitational redshift and relativistic precession exactly as general relativity predicts. The orbit is not a perfect ellipse, but rather an ellipse that slowly rotates, precessing due to the curvature of space-time. The M87 black hole, 6.5 billion solar masses, accretes far more vigorously than Sagittarius A star, despite its much larger mass. The Event Horizon Telescope image shows a bright, asymmetric ring, brighter on the bottom than the top. This asymmetry results from Doppler beaming. Material orbiting the black hole moves at relativistic speeds. The approaching side moving toward us appears brighter due to the beaming of radiation in the direction of motion. The receding side appears dimmer. The orientation of the brightness asymmetry reveals the direction of the black hole's rotation and the orientation of its spin axis. Additional observations in 2018 showed that the ring structure remains stable over time, though the detailed brightness distribution changes. The black hole also produces a powerful jet extending at least 5,000 light-years from the galactic core. The jet appears to launch from near the black hole's rotation axis, consistent with models where magnetic fields extract energy from the rotating black hole or the inner accretion disk. Recent discoveries have expanded the known population of black holes into new mass ranges. In 2019, the LIGO-Virgo collaboration detected gravitational waves from a merger involving a black hole of 23 solar masses and a companion of 2.6 solar masses. The smaller object falls into the so-called mass gap between the heaviest neutron stars, around 2 solar masses, and the lightest previously known black holes, around 5 solar masses. The existence of this object challenges theories of stellar evolution and supernova explosions. Massive stars are thought to either explode completely, leaving no remnant, or collapse to form black holes of at least 5 solar masses. Finding an object in the gap suggests that either our understanding of supernova is incomplete, or that black holes can form through different mechanisms, possibly from mergers of neutron stars or earlier generations of stellar evolution. Intermediate mass black holes, with masses from hundreds to hundreds of thousands of suns, remain elusive. These objects should exist as bridges between stellar mass and supermassive black holes, but clear detections are rare. In 2020, the LIGO-Virgo collaboration announced the detection of gravitational waves from a merger that produced a black hole of 142 solar masses, the first definitive intermediate mass black hole. The progenitor black holes had masses of 66 and 85 solar masses. The 85 solar mass black hole itself is puzzling, because stellar evolution models predict that stars massive enough to produce black holes in this mass range should instead explode completely without leaving a remnant, a phenomenon called pair instability supernova. The detection suggests that either pair instability does not operate as expected, or that these black holes formed through mergers of smaller black holes in earlier generations. Similar phenomena in different astrophysical contexts show how time dilation manifests across scales. Neutron stars, while not black holes, create gravitational fields strong enough to produce measurable time dilation. A neutron star with 1.4 solar masses compressed into a sphere just 20 kilometers across has a surface gravitational redshift factor of about 1.15. This means that a photon emitted from the surface with a wavelength of 500 nanometers, green light, arrives at a distant observer redshifted to about 575 nanometers, yellow-orange light. Clocks on the neutron star surface tick about 15% slower than clocks far away. This is a huge effect by everyday standards, but modest compared to the time dilation near black hole event horizons, where factors of thousands or millions apply. The statistical distribution of black hole properties reveals patterns. Stellar mass black holes in X-ray binaries show a clear preference for masses between 5 and 20 solar masses, with a sharp drop-off above 20 solar masses and essentially none below 5 solar masses except for the mass gap object mentioned earlier. This distribution reflects the masses of the progenitor stars and the physics of core collapse. More massive stars produce more massive black holes, but the relationship is not linear. Much of the star's mass is expelled during the supernova explosion or earlier mass loss phases. Supermassive black holes show a different distribution. Most galaxies with substantial bulges contain supermassive black holes, with masses correlated to the bulge properties. The correlation suggests that black holes and galaxies grow together through feedback processes that regulate both. But the scatter in the correlation is significant. Some galaxies have black holes more massive than expected. Others have black holes that seem too small. These outliers hint at different formation histories or evolutionary paths. Unexplained aspects include the formation mechanisms for the first supermassive black holes in the early universe. Quasars powered by billion solar mass black holes appear in observations of the universe when it was less than 1 billion years old, just 7% of its current age. Growing black holes from stellar mass seeds to 1 billion solar masses in less than 1 billion years requires sustained accretion at or above the Eddington limit. But accretion at these rates should blow away the surrounding gas through radiation pressure, choking off further growth. Various solutions have been proposed. Perhaps the first black holes formed from the direct collapse of massive gas clouds in the early universe, creating seeds of thousands or hundreds of thousands of solar masses rather than just tens of solar masses. Or perhaps the Eddington limit can be exceeded temporarily in dense environments. Or perhaps early black holes grew primarily through mergers rather than accretion. Observations have not yet distinguished between these scenarios. Ongoing research focuses on measuring black hole spins with greater precision and for larger samples. The spin encodes information about formation and growth. A black hole formed from a single collapsing star might have low spin. A black hole grown primarily through accretion of gas should have high spin aligned with the accretion disk. A black hole grown through mergers might have spin determined by the orbital angular momentum of the mergers, potentially misaligned with the host galaxy. Large surveys with future X-ray missions will measure spins for hundreds of black holes, revealing whether most rotate rapidly or slowly, and whether the spin direction correlates with galaxy properties. Tidal disruption events, where stars wander too close to supermassive black holes and get shredded, offer unique opportunities to study black holes that are otherwise quiescent. The rate of tidal disruptions depends on the stellar density near the black hole and the black hole mass. Observations suggest that disruptions occur in a given galaxy roughly once every 10,000 to 100,000 years. Modern surveys observe thousands of galaxies continuously, detecting several disruptions per year. Each event produces a bright flare lasting months to years as the stellar debris forms an accretion disk and radiates. The flare spectrum and light curve evolution encode information about the black hole mass and spin and the structure of the disrupted star. Follow-up observations with X-ray and optical telescopes track how the debris evolves, testing models of accretion disk formation in real time. The diversity across these systems confirms that while time dilation near each black hole operates according to the same underlying physics, the specific manifestations depend on mass, spin, accretion rate, and environment. A stellar mass black hole with rapid spin creates different observational signatures than a slowly rotating supermassive black hole. But in every case, matter orbiting close to the horizon experiences time flowing at a different rate than matter far away. The ratio of time dilation factors can reach thousands or millions for the innermost orbiting material compared to distant observers. This is not subtle. This is the dominant effect shaping the observed emission from regions near the event horizon. Yet our observations always come from the perspective of distant observers, watching from outside the strong gravitational field, which raises questions about perspective effects and observational biases that fundamentally shape what we can and cannot learn about black holes. Every observation we make of black holes comes from a fundamentally limited perspective. We observe from outside, from outside, from positions of safety far from the event horizon where space-time remains relatively flat and time flows at familiar rates. We never see the journey from the perspective of an infalling observer. We cannot receive signals from inside the event horizon. The entire observational framework for studying black holes rests on measurements made in regions where gravitational effects, while detectable, remain far from the extremes experienced near the horizon itself. This creates unavoidable biases in how we understand these objects. We map the territory from the outside, inferring interior conditions from external effects, never able to directly sample the regions where time dilation becomes truly extreme. The perspective dependence runs deeper than simply lacking access to certain regions. The very concept of simultaneity breaks down near event horizons. Events that appear simultaneous to a distant observer occur at wildly different times, according to an infalling observer's clock. Consider someone falling toward a black hole while we watch from far away. When we see them approach the horizon, we are seeing light that left them at progressively earlier times by their own clock. The last photon that reaches us before they cross was emitted just before the crossing, but that photon takes an extraordinarily long time to climb out of the gravitational well. From our perspective, the crossing appears to take infinite time. We see them slow down, redshift, and fade. But they experience the crossing in finite proper time, seconds or minutes depending on the black hole mass. Both descriptions are accurate within their respective reference frames. There is no universal truth about when the crossing occurs. The timing depends entirely on who is measuring. This observer dependence affects every measurement we make. When we observe X-rays from the inner accretion disk, we are detecting photons that have climbed out of the gravitational well, redshifted by the climb, and time-dilated by the source motion. The photons we detect were emitted earlier in the orbiting material's reference frame than they arrive in ours. The orbital frequency we measure is lower than the frequency measured in the orbiting material's frame by exactly the time dilation factor. For material at the innermost stable circular orbit around a rapidly spinning black hole, this factor can exceed 2. The orbit that appears to take 2 milliseconds from our perspective takes only 1 millisecond in the material's own frame. We infer the 1 millisecond period from the 2 millisecond observation by applying our understanding of time dilation. But we never directly measure the 1 millisecond period. We always observe the dilated version. The limitations become more severe when we try to study regions very close to the horizon. The extreme gravitational redshift makes photons from these regions shift to longer wavelengths and lower energies. A photon emitted with X-ray energy might arrive as a radio wave after climbing out from close enough to the horizon. The energy decrease means fewer photons reach our detectors with sufficient energy to be recorded. The signal fades not because the source stops emitting, but because the emitted radiation redshifts beyond our ability to detect it. This creates a detection horizon, a boundary within which sources become too faint to observe, regardless of how bright they actually are in their own reference frame. The detection horizon depends on our instrument sensitivity and sits outside the event horizon itself, sometimes substantially outside for sources emitting at wavelengths that redshift into regions where our detectors are insensitive. Our observations might be influenced by selection effects that favor certain types of black holes or certain states of accretion. We detect black holes most easily when they are actively accreting matter and emitting radiation across wavelengths our instruments can observe. A quiescent black hole accreting little or no matter produces minimal emission and remains invisible unless we can detect its gravitational effects on nearby stars or gas. Sagittarius A star was identified through the orbital motion of stars around it and through radio emission from the small amount of material falling in. If it were accreting at rates typical for quasars, it would outshine every star in the galaxy. Most black holes probably accrete at low rates most of the time, with brief episodes of higher accretion during galaxy mergers, tidal disruption events, or other transient phenomena. Our surveys preferentially find the active systems, creating a biased sample that might not represent the typical black hole population. The concept of a bubble or local effect applies differently here than in cosmology, but remains relevant. We observe black holes within our cosmological horizon, the sphere beyond, which light has not had time to reach us since the Big Bang. The observable universe contains perhaps 100 billion galaxies, most with central, supermassive black holes, plus countless stellar mass black holes formed from massive stars over cosmic history. But this represents only the portion of the universe we can see. If the universe extends far beyond our horizon, as most cosmological models suggest, then the total number of black holes vastly exceeds what we can observe. Our sample is local in cosmic terms, drawn from a sphere just 46 billion light-years in radius, in a possibly infinite cosmos. Whether this local sample represents the full diversity of black holes depends on whether the universe is homogeneous on large scales, a question tied to fundamental cosmological principles. The debate over typicality versus specialness has ancient roots. For millennia, humans assumed Earth occupied a privileged position at the center of creation. Nicholas Copernicus, publishing his heliocentric model in 1543, displaced Earth from the center of the solar system to just another planet orbiting the Sun. Subsequent discoveries displaced the Sun from the center of the galaxy from the center of the universe, and even the universe from uniqueness, as theories of cosmic inflation suggest countless universes might exist in a vast multiverse. Each step has reinforced the Copernican principle, the idea that we do not occupy a special location. We should expect to be typical observers in a typical place, rather than privileged observers in a special place. Applying this principle to black holes suggests that the ones we observe should represent typical examples rather than rare extremes. The distribution of masses, spins, and accretion rates in our local sample should reflect the distribution in the larger universe. If we find that most observed supermassive black holes rotate rapidly, we might infer that rapid rotation is typical. If we find correlations between black hole mass and galaxy properties holding across our sample, we might extend those correlations to unobserved galaxies. But the principle has limits. Selection effects can make our sample unrepresentative. We might preferentially detect the most massive black holes or the most actively accreting ones, even if these represent rare extremes. Distinguishing typical from special requires understanding our observational biases well enough to correct for them. Cosmological principles at stake include the assumptions of homogeneity and isotropy that underlie standard cosmology. If the universe is homogeneous on large scales, then black holes should show similar properties everywhere. The mass function of stellar mass black holes should be the same in distant galaxies as in the Milky Way. The relationship between supermassive black holes and their host galaxies should hold across cosmic time. Violations of these expectations would suggest either that the universe is not homogeneous or that our understanding of black hole formation and evolution is incomplete. So far, observations support homogeneity. Distant quasars show properties consistent with local active galactic nuclei scaled to different cosmic epochs when galaxies were younger and gas-rich. Stellar mass black holes detected through gravitational waves show mass distributions consistent with expectations from stellar evolution models applied to observed star populations. Anthropic considerations enter when we ask why the universe allows black holes to exist at all, and why they have the properties they do. The formation of stellar mass black holes requires stars massive enough to undergo core collapse, which requires nuclear fusion to produce elements heavier than hydrogen. Nuclear fusion requires the strong nuclear force to have sufficient strength to bind protons and neutrons into stable nuclei, while the electromagnetic force has sufficient strength to make stars hot and dense. These forces have the values they do for reasons we do not fully understand. If the force strengths were slightly different, stars might not form, or they might all explode completely without leaving remnants, or they might collapse directly to black holes without shining, for billions of years. The fact that we observe a universe with long-lived stars and black holes both present might reflect anthropic selection. Observers can only exist in regions where conditions allow complex chemistry and long timescales for evolution. Such regions might necessarily include both stars and black holes as byproducts of the same physical laws. Future surveys will dramatically expand our sample of observed black holes and test whether our current understanding based on relatively few well-studied systems holds for larger populations. The Vera C. Rubin Observatory, conducting the Legacy Survey of Space and Time, starting in 2025, will observe the entire visible sky every few nights for 10 years. The survey will discover tens of thousands of transient events, including tidal disruption events, supernovae that might form black holes, and potentially electromagnetic counterparts to gravitational wave sources. The rapid cadence allows tracking how these events evolve in real time, testing models of black hole accretion and jet formation with far larger samples than currently available. The survey will also discover quasars at redshifts beyond 7, corresponding to epochs when the universe was less than 800 million years old, probing how the first supermassive black holes formed and grew. X-ray surveys with future missions like New Athena will observe black holes in thousands of galaxies across a range of masses, spins, and accretion states. These surveys will measure how black hole properties correlate with galaxy properties across cosmic time, testing whether the relationships we observe locally hold universally. They will also search for intermediate mass black holes in globular clusters and dwarf galaxies, filling in the mass gap between stellar and supermassive black holes. Detecting even a few clear examples of intermediate mass black holes would constrain formation scenarios and reveal whether there is a continuous mass spectrum or distinct formation channels for different mass ranges. Gravitational wave detections will continue to accumulate, potentially reaching hundreds or thousands of black hole mergers over the next decade, as detector sensitivity improves and new facilities like the Einstein Telescope and Cosmic Explorer come online. These ground-based detectors will observe stellar mass black hole mergers out to redshifts exceeding 2, when the universe was about 3 billion years old. The statistics of merger rates, mass distributions, and spin alignments will reveal how black holes form and evolve in different galactic environments. LISA in the will detect supermassive black hole mergers across the observable universe, providing direct measurements of masses and spins for the largest black holes that have ever merged. These observations will test whether black hole growth occurs primarily through mergers or accretion, and whether the merger rate evolves with cosmic time as galaxy merger rates change. Black holes serve as natural laboratories for testing general relativity in regimes inaccessible in terrestrial experiments. The gravitational fields near event horizons exceed anything we can create artificially by factors of billions or more. Time dilation factors of thousands require orbital velocities approaching the speed of light in gravitational potentials so deep that a significant fraction of rest mass energy becomes gravitational potential energy. No particle accelerator reaches these energy densities. No laboratory can create space-time curvatures approaching those near black hole horizons. We rely on observations of astrophysical systems to test whether general relativity continues to hold in these extreme conditions. Every test so far confirms Einstein's theory. The orbital dynamics of stars around Sagittarius A star match the predictions of general relativity with precision, limited only by measurement uncertainties. The gravitational wave signals from black hole mergers match numerical relativity simulations to astonishing accuracy. The shadow of the M87 black hole has the size and shape predicted for a Kerr black hole with the inferred mass and spin. The iron line profiles from accretion disks show the broadening and skewing expected from Doppler shifts and gravitational redshift in the Kerr metric. Across wavelengths, techniques, and source types, the observations support general relativity. No confirmed deviation has been detected despite decades of searching with increasingly sensitive instruments. This success creates a puzzle. General relativity is almost certainly not the final theory of gravity. We know it must break down where quantum effects become important, at densities and curvatures approaching the Planck scale. Yet all our observations occur in regimes where general relativity should work, far from the Planck scale, even near black hole horizons. The event horizon of a stellar mass black hole has a radius of kilometers, enormously larger than the Planck length of 10 to the minus 35 meters. We test general relativity successfully because we observe only regions where it should apply. The regimes where it fails, inside black holes approaching the singularity, remain hidden behind the event horizon. Nature appears to protect us from observing the breakdown of our theories through cosmic censorship. The idea that singularities are always clothed by event horizons and never naked to external observation. The limitations of our observational perspective mean we can measure time dilation near black holes only indirectly. We cannot send a clock close to the horizon and retrieve it to compare elapsed times. We cannot receive signals from observers who cross the horizon to learn what they experience. Every measurement requires inference from external effects like redshifts, orbital frequencies, and emission spectra. The extreme time dilation we calculate from general relativity remains a theoretical prediction confirmed indirectly through its consequences, but never measured directly. This does not make it less certain. The consistency across independent observations using different techniques provides strong evidence. But it highlights that our understanding of extreme gravity rests on a theoretical framework confirmed by its ability to predict observations, not on direct measurements of the most extreme regions. The black holes we observe today represent early chapters in cosmic history, fleeting moments in a story that extends across timescales so vast they dwarf the current age of the universe. The cosmos is 13.8 billion years old. Stars have been forming and dying for most of that time. Black holes have been accumulating for billions of years, but if current physics holds, the era of stars will end long before the era of black holes does. The universe will continue expanding, cooling, diluting. Star formation will cease when the last reservoirs of hydrogen gas are exhausted or dispersed beyond the density required for gravitational collapse. That endpoint might arrive in a few trillion years, a timescale hundreds of times longer than the universe has existed so far. After the last stars fade, the universe will be dominated by stellar remnants, including white dwarfs, neutron stars, and black holes, along with planets, asteroids, and diffuse gas too thin to form new stars. Black holes will outlast everything else by incomprehensible margins. A stellar mass black hole with 10 solar masses evaporates through Hawking radiation on a timescale of roughly 10 to the 67 years. That number contains 67 zeros. For context, the current age of the universe is about 10 to the 10 years, a 1 followed by 10 zeros. The ratio between the black hole evaporation time and the current cosmic age is 10 to the 57, a billion. The universe would need to age by that factor before even a single stellar mass black hole disappeared. Supermassive black holes take even longer. A billion solar mass black hole persists for approximately 10 to the 98 years, a timescale that utterly defeats human comprehension. The numbers stop having intuitive meaning. They become abstractions, symbols representing durations so prolonged that nothing from our experience provides analogy. During these vast intervals, the black holes themselves change only slowly. They radiate, losing mass particle by particle as quantum fluctuations near the horizon produce Hawking radiation. The process accelerates as the black hole shrinks. Smaller black holes have higher surface gravity and emit more energetic radiation. A black hole the mass of a mountain would evaporate in a few billion years, roughly the lifetime of a star like the Sun. A black hole the mass of a large asteroid would evaporate in seconds, exploding in a burst of high-energy particles and gamma rays. But astrophysical black holes, formed from stars or grown through accretion in galaxy centers, start with masses far too large for this acceleration to matter on any timescale relevant to current cosmic conditions. They sit in the dark, barely radiating, waiting out epochs incomparably longer than the age of stars and galaxies. The ultimate fate of these objects depends on whether protons decay. The standard model of particle physics treats protons as stable, enduring forever without decaying into lighter particles. But many theories that attempt to unify the fundamental forces predict that protons should decay with half-lives, around 10 to the 35 years or longer. Experiments searching for proton decay have found no evidence, placing lower limits on the proton lifetime exceeding 10 to the 34 years for certain decay modes. If protons do decay, then all atomic matter will eventually disintegrate. Stars, planets, even the cold remnants of dead stars will dissolve into radiation and lighter particles over timescales of 10 to the 40 years or so. Black holes would remain, fed slightly by the occasional particle wandering too close, but otherwise isolated in an increasingly empty universe. Time dilation offers a theoretical escape from these timescales. If you could position yourself very close to a black hole's event horizon without falling in, you would experience time flowing at a vastly reduced rate compared to the distant universe. Hover near the horizon for what feels like a year while trillions of years pass outside. The universe ages around you. Stars burn out, galaxies disperse. But you age slowly, experiencing the deep future compressed into a manageable, subjective duration. The energy required to maintain position against the black hole's pull is enormous, increasing toward infinity as you approach the horizon. But in principle, with sufficient energy reserves, you could use a black hole as a time machine to the far future, watching the cosmos evolve at accelerated rates from your time-dilated perspective. What civilizations, if any, survive to those distant epochs might do with black holes remains speculative but constrained by known physics. A sufficiently advanced civilization could extract energy from a rotating black hole through the Penrose process, lowering material into the ergosphere and using the frame-dragging effect to accelerate some of it back out with more energy than it had going in. The excess energy comes from the rotational energy of the black hole itself. Repeating this process could, in principle, extract a significant fraction of the black hole's rotational energy, slowing its spin while providing power for the civilization. Alternatively, a civilization could harvest the energy from matter falling into the black hole by capturing radiation from the accretion disk before it crosses the horizon. A perfectly efficient system could convert up to 42% of the infalling rest mass into usable energy for a maximally rotating black hole, far exceeding the few percent efficiency of nuclear fusion. Such civilizations would experience time differently depending on where they choose to live. A habitat far from the black hole would age at the standard rate. A habitat closer in would age more slowly. Communication between the two would be complicated by time dilation. A message sent from the close habitat and received at the distant habitat would appear slowed down, stretched in time by the time dilation factor. A response sent back would appear sped up, compressed in time. Coordinating activities across regions with different time flow rates would require careful accounting for these relativistic effects. The civilization would effectively split across different temporal streams, all present in the same spatial location, but experiencing time at different rates. Whether any observers, intelligent or otherwise, will exist to witness the black hole era seems doubtful given current understanding of cosmology and biology. Life, as we know it, requires energy sources and gradients, structures out of thermodynamic equilibrium. Stars provide such gradients. A planet orbiting a star receives energy, hosts chemical reactions, radiates waste heat to space, and maintains complex structures. As stars die out, these energy sources disappear. The universe approaches thermal equilibrium, a state of maximum entropy where no useful work can be extracted and no gradients drive complexity. Whether life could exist in such conditions using alternative energy sources, perhaps extracting the minuscule energy from Hawking radiation or from the decay of dark matter particles, if they are unstable, remains an open question at the boundary of physics and biology. The question of other observers connects to the possibility that consciousness or intelligence could exist in forms we do not currently imagine. If observers require biological substrates, then they likely require stars and planets and chemistry, all transient features of the relatively young universe. But if observers could exist as patterns in other substrates, perhaps electromagnetic fields or quantum states of matter in extreme conditions, then the future might hold possibilities we cannot currently conceive. The universe might develop new kinds of complexity as it ages, structures that use the sparse remaining energy to organize information and experience existence in ways completely alien to biology. This is speculation beyond science, touching on philosophy and metaphysics. We have no evidence for such possibilities, but the universe has surprised us before with phenomena we did not anticipate. Meta-questions about knowledge itself emerge when contemplating these vast timescales and extreme conditions. How can we know anything about events occurring 10 to the 67 years in the future? We extrapolate current physical laws, particularly general relativity and quantum mechanics, across timescales trillions of times longer than we have tested them. The extrapolation assumes that these laws do not change, that constants remain constant, that the universe continues to behave according to rules we have inferred from observations spanning just decades or, at most, centuries. This assumption might fail. New physics might emerge at intermediate scales. The vacuum might decay into a lower energy state, restructuring space-time in ways that make current predictions irrelevant. The expansion of the universe might reverse if dark energy evolves in ways we do not expect. Our confidence in these predictions is not absolute. It is provisional, grounded in our current best understanding, but subject to revision as knowledge improves. Yet we make the predictions anyway, because extrapolating from known laws is the best we can do. The alternative is to abandon any attempt to understand the deep future, to declare it unknowable because we cannot directly observe it. That seems premature. The same laws that successfully predict outcomes of laboratory experiments and explain astronomical observations should apply at later times unless we have reason to think otherwise. We treat the predictions as probable but not certain, useful guides to what might happen rather than definitive statements about what will happen. The difference matters intellectually, even if it makes no practical difference, given that we will not exist to witness the outcomes. Philosophical synthesis of these ideas returns to fundamental questions about time, existence, and observation. Time is not what it seems. It flows differently in different places. It can be stretched and compressed by gravity. It is observer-dependent, with no universal now spanning all of space. These insights from relativity challenge the naive view that time is a simple, linear progression from past to future, the same everywhere. Instead, time is a dimension woven together with space into a unified fabric that warps and curves in response to mass and energy. Every massive object carries its own temporal distortions. Every observer traces a unique path through space-time, accumulating proper time according to the geometry along that path. Existence near a black hole forces confrontation with these realities. The extreme time dilation makes the difference between one observer's experience and another's not a subtle correction, but a factor of thousands or millions. 1 second for you becomes 10,000 years for someone else. The disconnect is so severe that the two perspectives lose synchronization. You cannot talk about what is happening now in both reference frames simultaneously. Now for you, and now for them refer to different events, different slices through the four-dimensional structure of space-time. This is not a failure of communication or measurement. This is the structure of reality itself, revealed by probing extreme gravitational conditions. The question of observation and measurement threads through all these considerations. We observe black holes from outside. We infer their properties from the behavior of matter and light around them. We calculate what happens near the horizon using general relativity. We predict time dilation effects and confirm them indirectly through redshifts and orbital dynamics. But we never directly experience the extreme conditions we describe. We remain distant, safe, observing from regions where space-time is relatively flat. The most extreme time dilation, the 1 second to 10,000 years scenario, remains a prediction confirmed by mathematical consistency and indirect measurements, but never tested by actually sending something close to the horizon and retrieving it to compare clocks. This does not diminish the confidence in the prediction. The theoretical framework has been tested exhaustively in accessible regimes and passes every test. Extrapolating to extremes follows logically, but it highlights the limits of direct knowledge. Perhaps the deepest lesson concerns humility about our place in space-time. We are local observers in both space and time. We occupy a small region of the observable universe during a brief epoch of its history. The stars we see are temporary. The galaxies will disperse. The black holes will evaporate. Even space-time itself might not be fundamental, potentially emerging from deeper structures we have not yet discovered. Our knowledge is provisional, constructed from observations made during this particular epoch, using instruments sensitive to particular wavelengths and phenomena. We extrapolate to understand what we cannot directly observe. We use mathematics to reach beyond immediate experience. This is the power of science, extending knowledge beyond direct perception. But it also means we remain aware of what we do not know and cannot directly access. Returning to the opening theme, the extreme time dilation near black holes stands as perhaps the clearest example of how gravity reshapes reality itself. 1 second for you, 10,000 years for someone watching from far away. This is not a thought experiment or a mathematical curiosity. This is physics confirmed by every observation we have of how time flows in gravitational fields. The effect scales from the tiny corrections required for GPS satellites to function properly, just microseconds per day, to the extreme factors of thousands or millions near black hole event horizons. Every massive object creates these distortions. Every observer experiences their own time, distinct from the time of others. The universe does not have a single clock ticking forward uniformly everywhere. It has countless clocks, each following its own path, each accumulating time according to the geometry of space-time along that path. Black holes represent endpoints of gravitational collapse, regions where space-time curves so severely that not even light escapes. They are laboratories for testing physics in conditions we cannot create artificially. They are bridges to understanding quantum gravity, the unification of general relativity and quantum mechanics that remains just beyond our grasp. They are monuments to the power of mathematics to describe reality, predictions made in 1915 and confirmed a century later through observations of shadows, gravitational waves, and the dynamics of matter spiraling toward oblivion. And they are reminders that the universe is stranger and more subtle than everyday experience suggests. Time is not absolute. Space is not static. Gravity is not a force, but the curvature of the fabric of existence itself. If this journey through the warping of time near black holes spoke to you, consider subscribing to join us for more explorations into the cosmos. There are countless mysteries waiting to help you drift off, from the quantum foam underlying space-time to the possibility of other universes beyond our own. Leave a like if you found peace in contemplating these vast scales and extreme physics. And good night. Wherever you are in this universe, experiencing time at your own rate, aging second by second as the cosmos ages around you at its own relentless pace, indifferent to our perceptions, but knowable through the patient application of reason and observation.